This video will cover basic amplifier parameters and characteristics. You will see how the circuits are designed to establish the required operating voltage for common circuits like the small signal amplifiers, power amplifiers, and operational amplifiers. When a semiconductor device is operated in a switching mode, it is being used as a digital device. When the devices are operated linearly, they are being used as analog circuits. The most commonly used analog circuit is the amplifier. The amplifier is represented by a triangular symbol, which may be used to represent discrete component circuits or a multi-stage integrated circuit amplifier. There are many circuit configurations which exist between these two extremes. Amplifiers are used to reproduce small input signals. Amplifiers may be powered by batteries or electronic power supplies. The characteristics of all amplifiers may be described in terms of a few basic parameters: gain, impedance, and distortion. The gain of a circuit is a measure of the increase in signal level from the input to the output. Gain may be measured in terms of current, voltage, or power. The unit of measurement for gain is the decibel. In general, gain equals the output divided by the input. When gain is expressed in decibels, the equations require the use of logarithms to the base 10. For voltage, the equation in gain in decibels equals 20 log 10 times voltage out divided by voltage in. For current, the equation is gain in decibels equals 20 log 10 times current out divided by current in. And for power, the equation is gain in decibel equals 10 log 10 times power out divided by power in. Because gain is only a ratio of two like quantities, it has no absolute unit of measurement. The decibel is the relative unit used, indicating the relative differences in the two electrical measurements. The amplifier's input and output impedance is another important circuit characteristic. The amplifier receives its input signal from a prior circuit called a stage, and it delivers its output to a succeeding stage or a load device. The amplifier receiving the signal must not present too much of a load to the signal source, which may be another amplifier's output. If the load becomes too great, the signal source will be unable to provide enough signal power to drive the amplifier input, and the amplifier's output will be pulled down to zero. The ideal amplifier will have an infinite input impedance, requiring no current from the signal source. The best power transfer and lowest distortion is achieved when the amplifier's output impedance equals the input impedance of the circuit being driven. The third parameter of the amplifier is called the distortion. As you recall, the amplifier is designed to increase the amplitude of the input signal by its gain factor. Since there are no perfect components or circuits, all amplifiers will distort the input signal. Distortion may occur in frequency, phase, or in the amplitude of the signal. Frequency distortion occurs when a certain range of frequencies are amplified by a different amount than others. This distortion is the result of the capacitance and inductance used throughout the circuit. The degree of frequency distortion in the amplifier is described by its frequency response specifications. The frequency response specifications indicate the relative output over a specific frequency range. Phase distortion, on the other hand, will occur when certain bands of frequencies require different amounts of time to pass through an amplifier. Even though the sine wave consists of a single frequency, other more complex waveforms are derived by mixing the sine wave with even or odd harmonic waves of the sine wave. For the amplifier to produce an exact reproduction of the input signal, it must not delay any part of the signal, or the signal will become distorted. Amplitude distortion occurs when the output signal is not a faithful reproduction of the input signal or wave shape. This may be caused by the amplifier being driven into saturation and clipping the peaks of the signal. There are three other types of amplitude distortion: harmonic, intermodulation, and transient intermodulation. Harmonic distortion occurs when unwanted frequencies are added to the amplified signal. Harmonic distortion is impossible to completely eliminate in practical amplifying devices. This type of distortion is usually generated during the process of amplification. The total harmonic distortion will be given as a percentage of the output signal. Intermodulation distortion is a result of one sinusoidal component modulating another. This creates a new frequency which becomes a part of the output signal. Transient intermodulation distortion will occur when the input signal changes so rapidly that the amplifier cannot keep up. This usually results in distortion on the rise time part of the wave shape. As we have seen, the ability of an amplifier to deliver a signal must be matched to the requirements of the load being supplied. The circuit used to couple the power to the load will generally be a power amplifier. The power amplifier is usually fed by voltage amplifier stages. The voltage amplifier is used to boost the incoming signal to a level sufficient to drive the power output stage. Voltage and power amplifiers have significant differences from one another. Therefore, we will examine them separately. In order to amplify a signal, the device must be capable of producing a large increase in its output voltage and/or current in response to a small change at its input. The signal at the input will control the device so that it produces a larger signal at the output. The earliest electronic amplifying device was the vacuum tube. The input signal is applied at the control grid, which is placed between the cathode and plate of the vacuum tube. The input signal controls the current flow between the cathode and plate. The large plate current is much larger than the current supplied by the input signal. Today, however, most general-purpose amplifiers use semiconductor devices to provide amplification. The bipolar transistor and field effect transistor will perform the same function as the vacuum tube, but they do it much more efficiently. The semiconductor will use far less current for the same amount of amplification. Semiconductor devices used in power amplifiers differ from those used in voltage amplifiers, both physically and electrically. This is because power amplifying devices are physically larger and are designed to operate with higher voltage and current levels than those required for the smaller signal amplifiers. Other than this, the basic concept of both types of amplifier circuits are quite similar. When working with amplifier circuits, the DC power supply must satisfy three requirements. It must supply sufficient energy to the amplifier stage. It is used to set the operating point of the device for proper operation. And it is used to set the electrical operating conditions of the amplifier. The DC circuit used to set the operating conditions of the amplifier is referred to as the bias circuit. The bias circuit should prevent changes in the operating conditions even if the amplifying device's characteristics change during normal circuit operations. A well-designed circuit will provide for a stable circuit operation. The load resistor, RL, which is attached to the output of the amplifier along with the power supply, is used to set the power output limitations of the amplifier. The output signal current cannot exceed the power supply voltage divided by the load resistor. This can be better illustrated using a simple transistor circuit. As you can see, the maximum current flow through the transistor is limited by the load resistor RL. When the current flow through the transistor is stopped, the voltage drop across the emitter collector of the transistor will equal the power supply voltage. Between the saturation and cutoff limitations of the transistor, there are an infinite number of current levels. Therefore, the current flowing in the output circuit at any instant must be between these two limits. Here we see a typical common emitter family of characteristic curves. At point A, we see that the transistor will conduct a little over 3 milliamps of current and develop a 10-volt drop across the collector emitter of the transistor with a 20 microamp bias current being applied at the base. By using Ohm's law, R equals E over I, we see that the transistor is developing a resistance of approximately 3,226 ohms. If the voltage drop across the transistor is held constant and the base current is increased to 50 microamps, we see that the collector current will increase. For this to happen, the transistor's emitter to collector resistance had to decrease when the base current was increased. By knowing the maximum collector current and the maximum collector emitter voltage drop, a DC load line can be drawn. The maximum collector current is developed when the transistor is at its saturation point, and the maximum collector emitter voltage drop occurs when the transistor is at its cutoff point. Typical amplifier operation will usually be somewhere along the DC load line between saturation and cutoff. When no input signal is applied, the amplifier's operating condition will be at a specific point on the DC load line called the quiescent operating point, or simply its Q point. The Q point is set by three parameters. First, the collector to emitter voltage, the collector current, and the base current. When the input signal is applied at the base current will change, and this will result in the other two parameters changing along the DC load line. When the base current increases, the parameter will shift up the DC load line, and when the base current decreases, the other two parameters will shift down the DC load line. Small signal amplifiers are designed to increase the amplitude of the incoming signal. To allow for the widest variations in amplitude, the Q point should be located at the midpoint of the DC load line. This allows the signal to fluctuate the maximum amount between these two extremes. Here we see another graph representing a characteristic curve of an amplifier between cutoff and saturation. Notice that the quiescent operating point, or Q point, is located at the midpoint of the linear portion of the curve. If the input signal is not too great, the circuit will operate in a linear mode and negligible amplitude distortion will occur. This is the operating point of a Class A amplifier. Power amplifiers, on the other hand, are usually operated as Class B amplifiers and are biased at the cutoff point on the curve. This allows only the increase of base current to become amplified. Since part of the signal is amplified in the lower knee of the curve, it will produce some distortion. Generally, power amplifiers are operated in the push-pull configuration. This allows for proper amplification of both sides of the signal. Another type of power amplifier is the Class C amplifier. The Class C amplifier is normally biased at 2.5 times the cutoff point. Obviously, the Class C amplifier introduces significant amounts of amplitude distortion and is not used for audio reproduction. Notice that Q1 only produces pulses of current into the tank circuit. Since Q1 does not continuously conduct a steady flow of current, it cannot faithfully reproduce the incoming signal. Class C amplifiers are normally used in oscillator circuits. Another class of amplifier operation is the Class AB1 and Class AB2. As you recall, the Class A amplifier was biased at the center of the linear portion of the characteristic curve, and this resulted in lower distortion. The Class B amplifier, on the other hand, was biased at the cutoff point on the curve, which resulted in a more efficient circuit, but also some distortion. It is possible to bias two transistors in a push-pull configuration somewhere between the Class A and Class B bias points. These amplifiers are called AB amplifiers. The Class AB amplifier is less efficient than the Class B and more efficient than the Class A amplifier. At the same time, they have less distortion than Class B amplifiers and more distortion than Class A amplifiers. There are two types of AB amplifiers, AB1 and AB2. The Class AB1 amplifier is biased a little more negative than the Class A operating point. In the Class AB2 amplifier, its operating point is biased even further negative than is the AB1. Normally, the AB2 bias point will be at the top of the lower knee of the characteristic curve. Since the AB2 is biased more negative than the AB1 operation, it requires more driving power than the AB1 amplifier.